And yeah, I mean, please take it away. Thank you.
Right, yeah, thanks so much. Today I'm going to talk about Dream Machine, and uh, I guess I'm not sure if many of you have seen this particular video. It basically shows you, some kind of a transition of a girl like gradually, smoothly transitioning into older and older, and this video actually got pretty viral after sharing it on Instagram. So probably got like a few hundred million views. And in there has been like video applications such as these with different types of things that are like entirely AI generated. So it's like gives you the like camera control and the consistency that were not there in like video models in the past year. And yeah, it was entirely made by Dream Machine. And we developed the model and like released it to public at around like June. At that time, it was pretty popular and broke the internet like a little bit. And as a result, our GPU were kind of burning, which is shown in this particular video. And some of the videos actually got lot of the views, such as like tens of millions of views. Actually, like just yesterday, we also like launched like a new dream machine, which basically allows you to like ideate, visualize, and create videos and share things and ideas over the world. So if you're interested, just use the like lumalabs.ai and check it out. So before we talk about the, like videos and, like video foundation models, let me first talk about like how Luma started, like as a company. So Luma initially started like working on things such as like 3D capture. So this is more related to like nerves and Gaussian splatting. So in this case, basically, one could try to capture like multi-view images of a scene. So for example, this is being captured by uh, like a drone footage. And basically then, because these things are relatively static, one can use some 3D reconstruction methods such as NeRF or Gaussian splatting to convert this into like interactive 3D scene. Uh, and then we also launched Genie, which is like 3D generation kind of like utility. So basically, it allows you to create 3D assets using text, and it extends on top of what have been done on 3D reconstruction via like Gaussian splatting. However, the more we like work on like 3D like reconstruction and 3D generation, we quickly realize that there is like an issue with like 3D. And that issue is basically this 3D data that's not very scalable. To put it into context, so for images and videos, there's like very like abundant resources online. So for example, Lion, this large scale like AI open network data set, was the one that was used to train the original like Stable Diffusion, and they claim to have collected about 5 billion images, and after some filtering, you can get to like basically like images about the order of uh, billions. And similarly for videos, there's a lot of videos that like like people have collected for data sets for research purposes. Another thing about images and videos is that it's relatively easy to create. So, for example, if you really want to, capture a like image or a video, you can just do it on the cell phone. So, like everyone has a cell phone nowadays, so there's a very abundance of such data. However, for 3D data, the thing is entirely opposite. So actually, if you check what are the kind of the size of the 3D data, maybe one of the biggest set of 3D data is this data set called Observerse XL. So basically, it claims that it has a like universe of 10 million 3D objects, and this is kind of as big as it can goes. And versus 1 billion, this is already like 100x difference. But what this doesn't actually tell you is that even within this 10 million objects, there are many objects that actually are rather low quality. So here, most of the high quality objects are shown. But if you actually do the like filtering to filter out like things that are like duplicated, are or have the same shape but different texture, or are just like not exactly correct, then you're not actually left with like not nearly 10 million like objects. It's more about like 1 million. So for example, if you look at the object verse data set about fish, there is actually a category of fish that have the same shape. However, if you actually want to use that fish in the training, you need to clean it because someone actually put a Rubik's cube, like a very tiny Rubik's cube, that is like beside the fish. And if you just directly use the data from the fish, you actually also include the Rubik's cube. So what I'm saying is that this kind of data is actually pretty like low quality, and even the like considering lowest quality is not that much. Another alternative is to do like 3D or multi-view captures. So for example, this data set called multi-view ImageNet, what they're trying to do is basically they hire a bunch of people that these people take their cell phone to like scan these like items in a multi-view fashion. And in some sense, this is also how like some of the capture like Luma capture data process like is there. And as a result, they hire a bunch of people and ended up with about 200K these like multi-view images. So similarly, another thing is that you need to actually kind of hire people and educate them about like how to actually capture these without like these objects being uh, becoming like usable in this like scenario. And so all I'm saying is that the 3D data is actually very hard to create, even the ones that there exist using like using artists or using like multi-view images is very scarce. And this is even just the shape and like appearance, and there's even less data with materials, articulations, and physics and so on. The algorithm that currently, powers 3D is also kind of like non-scalable. So for example, if we do like NERF or Gaussian splatting, we basically need to optimize a particular like procedure that reverses the rendering process. So in NERF and Gaussian splatting, there are assumed to be some type of rendering process, and basically one tries to like solve for this problem. And if you want to recreate the world, basically you also need to have the forward model of not only kind of rendering equations, but also materials, on fixed physics and articulations and causalities. And in order to solve this problem, you need to basically have something that's almost like a learnable game engine and try to optimize on top of the game engine to get all the features. So this also is like quite unscalable. So both the dataset and the algorithms are kind of like very non-scalable. So with that in mind, I really want to, go into a quick overview of like why like we as a company decide to kind of, work on videos. And, this is kind of driven by like multi-model diffusion models and how basically most of the text to 3D generation works are being done. And next, I will show some like emergent vision capabilities of Dream Machine, which, despite not being able to train on like 3D data, actually has some like interesting properties related to like 3D vision. So I guess everyone who have like heard about or like working on AI would have known that the most kind of popular and most scalable approach in like AI now is like autoregressive large language models. So the idea is quite simple. You have an input sequence, and the model tries to for each kind of sequence try to predict do next token prediction. So basically, in this earlier sequence, you try to give a probability of each of the possible word or token and give a probability of that. So in this case, you can see that the next word is supposedly dog, then the model gives a higher confidence over the word dog. And this is interesting because in language, these are tokenized to a discrete space. So then naturally people want to ask, like, what about continuous signals such as images? While autoregressive like models has also been tried for things like images as well as videos, it's actually less popular approach today. So today, people mostly try, things like diffusion models, which are proven to be a scalable kind of alternative to autoregressive large language models. So, the key idea of a diffusion model is quite straightforward. So instead of trying to, do this next word prediction, we actually try to, solve a different task, which is based on denoising. So in diffusion, we assume that from the left, which is a clean image, we actually gradually add more and more Gaussian noise to the image so that at the end, this original image gets entirely corrupted, and you basically cannot see what's the original image from at the right. And what a diffusion model does essentially is try to reverse this process. So basically, it is a learned model, and the learned model is mostly just trying to denoise the image. So basically, given the noisy image, how to recover the clean image. And basically, the task of a diffusion model is of next token prediction. Basically, it tries to denoise the image at different noise level with like regression. So basically, I have different noise levels. Some noise levels are like add a little bit of noise, and some noise levels add a bit more noise. And my model tries to do this denoising task at different noise levels. The model also knows the noise level. So basically, it knows like the standard deviation of the Gaussian noise that is provided, and that allows the model to, be dependent on the noise level and also do like mean prediction on the images. So, how does that like simple idea work for multimodal cases? So, in like actually most of these like models are powered by kind of one of the most amazing invention in the past 10 years in deep learning called attention. Basically, if we have text, let's say a corgi playing a flame throwing trumpet, and image, which is a corgi playing a flame throwing trumpet, in this data set, basically what like attention does is I try to create association with them. So basically, we know that for example, we have this query, which is the text tokens, and the keys are basically just the image patches. So it tries to kind of build this association across the text modality and the image modality. So on the right, we can see that on the top row there are like multiple words. Corgi playing a flame throwing trumpet, and the like left hand side we actually see different image patches. So here, basically, if you see the word corgi, it is being like highlighted by some of the four patches that contains the actual like corgi. And similarly, if you have the word flamethrowing, it actually shows you the top patch, which like has a little bit of like flamethrowing element in it. And similarly, basically the idea of like attention is try to build this connection implicitly through the different modalities. Of course, the actual representation of the inner workings of the query and keys are slightly different, but as the network becomes deeper, the model begins to learn to like uncover these associations, between like different modalities, like quite easily. And this is the building block behind stable diffusion. And like the most more of the key component, the actual model is a little bit more complicated than the above, but mostly the key components are just the self-attention and the cross-attention. So cross-attention tries to create association between text and the images, and in self-attention it tries to build this association between like images in itself. In some like newer architectures, there are more based on directly on self-attention. For example, Stable Diffusion 3 is based on just entirely self-attention with like different experts attending to different modalities. But you know, uh, like attention is a very key component in this. And on this right figure, I'm showing basically one of the earliest like papers that tries to do like purely like transformer or attention-based approach to uh, like image generation, and this work is called like Pixar Alpha. So yeah, as you can see here, we have like the text and the image trying to build this connections. So one may ask, okay, since Stable Diffusion work really well on images, and there's countless text to image models right now, based on like attention mechanism, it seems pretty ubiquitous. Can we actually just do multimodal diffusion models for 3D from 3D data? So there actually has been some works like based on this. And for example, in this paper called Maker Shape, it's trying to explicitly say that this is a 10 million scale 3D shape model. So as the name suggests, it is trying to learn a model based on like 3D data. And there's the 3D data is basically on the order of 10 millions. So it's actually pretty powerful in the sense that you can actually see that some of the application logs on the right. So there is, image to shape, so some texture image to shape, and it allows you to show some, like multi-view images to the shape. So there's multiple images of different views. It also can reconstruct into the shape. And there's also different cases which, such as like point clouds to shape. So basically, I give you the point cloud of the model, like you can reconstruct the shape. So actually, it's a pretty powerful like shape model. But you you can see that most of this like input types are something that we can easily generate from the 3D data. For example, these multi-view images and the point clouds. But these are not necessarily the case for text. So if I maybe input like a random text prompt, ask you to generate some asset, maybe it doesn't necessarily work so well. And as we have established earlier, the same like method was pretty scalable. So the problem is really not the method itself, but the scale of the data. Like I believe it was like a billion scale 3D data, you could actually do like text to 3D generation, but unfortunately the data is just not that much. So how do you actually make like text to 3D work? And I'm sure people are excited about like looking at the videos, but I'll get to it in a moment. So again, like what we have like on the diffusion community learned from the like language modeling community, we can just leverage like ideas like similar to attention from LLMs. We again leverage another idea from like large language models, such as this notion called supervised fine-tuning. And in supervised fine-tuning, what is done is this. So suppose that we have a lot of low quality but high quality text. So suppose these are just scraped from the internet. And you have a base like a model that initialized from random weights has been trained to do this simple next token prediction task. However, because this the data is high quality but low quality, it is actually doesn't necessarily like do some tasks very well, such as like answering your questions. Um, However, if you manage to, collect some demonstrations, so for example, like how humans will interact with each other, then you actually naturally have this like a data that is higher quality. However, it is like pretty tricky to collect this data at scale, so the amount of data is still like pretty low. So it's a high quality but low quantity data. So supervised fine-tuning is pretty easy in how it works. So you just simply initialize with the base model that you have trained on this lot of like low quality like raw text, and then you just apply the same next token prediction like algorithm to like optimize the weights, and that's basically it. And you can see that how this might lead to something that's quite interesting, like related to 3D. So uh, we just established that there's a lot of image data, and there's not a lot of like 3D data. However, for the like 3D generation problem, maybe 3D data is the category in which 3D is, is very high quality but low quantity, and images are the type of data that are like low quality but high quantity. So you instead in this case, for example, this work called MV Dream, essentially it leverages that idea. So basically, we'll take an image model that is trained from like billions of image data, and then you can do supervised fine-tuning on millions of 3D data. And the way they're trying to do this is by, instead of generating a single image, it actually tries to generate a multi-view image. So on the on the top on the left figure, it shows how it works. So on the top, it shows basically how this regular image training has been done. And basically, based on self-attention, this image like patch attends to different image patch within the same image. However, at the bottom, you can actually have like multi-view images. So there's multiple images within the, kind of the same network path. And so instead of having this single, self-attention that acts within the image, it simply just applies self-attention across like four images or the multi-view images. And also there's like additional camera conditionings that, tells the model like which like images which correspond to which view. Otherwise, if we don't provide this information, the model self-attention doesn't distinguish between these different views. And that's just about it. So this, simple kind of supervised fine-tuning procedure actually works on images and translates pretty well for like multi-view images. So on the right, you can actually see that this text to image model has been converted into a text to multi-view image model. So you can see things like astronaut riding a horse, or like an eagle carved out of wood, or like bulldog wearing a hat, and these kind of multi-view images. And of course, it is possible that some of these like appear in the some of these appear in the like like training set of the 3D data, but it's very unlikely to have like this kind of diversity. For example, astronaut riding a horse type of things. So we just established how we are going to get from like uh, you know, image model to a multi-view image model. So how do we go to 3D? So going to 3D is actually pretty straightforward. So because you already have like multiple views of the same image, you can actually use it to like do some like a 3D reconstruction again. So, but instead of like trying to solve this, like 3D reconstruction problems such as in NeRF and the Gaussian flattening, one could just also apply a transformer-based reconstructor. So basically, you train on this particular task where the input is multiple images and the output is some like 3D representation, such as a NeRF model. Of course, you can also just optimize the NeRF based on like multiple views, and you can also get a 3D model. But the you know once you have multiple view images, like getting a 3D model becomes like a problem that happens like after it. So then, what's how does it relate to videos? So, well, again, if you want to generate something that's even richer than 3D, then it is 4D, right? So in 4D, we have like three dimensions, height, like width, depth and time. And of course, in this case, I can say in order to generate 4D, I can first generate 3D, and then I use whatever that comes from the graphics community to convert that 3D into 4D. So for example, for a human, I do some like rigging, I code up some like animation, and I try to basically use human prior knowledge to drive it. However, as we can see earlier from the approach of image to 3D, uh, it would be quite natural to think maybe if we have this like uh time dimension that's being added, it should the real scalable solution should be videos to 4D. So with that in mind, we actually began to explore a video a bit more because it's seemingly the like only scalable solution that we can come about in terms of like generating 4D. So we went on this quest to train a video model, and as you can see, some of the results are actually pretty cool. So in particular, some of these cases actually can be done in this way. So you can actually like render like an image, and you put that image into this image to video pipeline, and then you can convert that into 3D back to the interactive scenes like in Gaussian splatting. So basically, the video, of course, is also a multi-view image if you decompose the frames. And this clearly shows that the model is actually learning some 3D things, because if it weren't 3D consistent, then you wouldn't be able to like dump it into a pipeline that basically does 3D reconstruction. So this video model actually does it, and it's pretty cool. And naturally, we also tried, image and video task on some kind of like data sets that are from the kind of like 3D construction community such as NeRF. And there's just multiple examples from like NeRF. And you can see that some of the cases, the model actually tries to imagine new details that were like otherwise like out of frame. So this is also quite interesting. So next, we want to show that basically, how from a 3D perspective, like what does the video model like actually learn? And what is the video model able to kind of just you know have some like emergent kind of understanding of the world around us, just by watching videos. Again, this is not based on any kind of 3D data or like multi-view data that I mentioned earlier. So for example, the model actually learns steps from like watching videos. So in this case, you can see that as the camera turns, the person in the front actually like is moving slower than the mountains like right behind her. So the model clearly knows that the mountain is at a distance, whereas the like person is closer. And similarly, this particular case is also the case that you have this particular subject in front, and there's the generations in the back. And similarly, there like even for like very abstract things, this actually works. So it's not like in the case of saying, well, it has to be a physical like possible object for this kind of notion of depth to work. Not really. In this case, it's basically based on like entirely just like abstract art, and so you wouldn't actually assign a physical kind of a depth in a physical depth just basically just doesn't make sense. But you can also see that as the circus that turns, it's actually giving you a sense of depth that is still consistent with what human believes. So this the notion of that's why I kind of quoted the notion of depth because in this abstract case, it's not really depth, but it's something like related to that. And similarly, you can actually have this, like generate some cool kind of camera transitions, as well as, like generate some things that were like normally speaking, not like not something that you would expect from a video model, like, back in the day. Another interesting property is, light transport. So I think in the graphics community, people spend years trying to investigate, how light transports, like onto the surface, across surfaces, and in on different materials. So in this particular case, what I want everyone to kind of look at is how, as the neon sign Luma turns on from like right to left, you can see how much like this light gets shined on the person's hair. So basically, as the sign, is at the center, of course, the more of this like brightness gets like redness gets like reflected onto the person. And as the kind of a sign goes to the right, it, actually, oh, sorry, goes to the left, it actually has more of this like red, like, brightness onto the like left side of the person. Another thing to note is that the person is wearing a like very heavy like yellow glasses, and as she turns, you can see some of the like you know refraction like coming out of this of the glasses, and as you can see, it's a yellow pair of yellow glasses, and yeah, it's like that. So clearly, the model is able to kind of recreate some of the kind of non-trivial scenes that, again, one would, if you want to recreate this entire scene in like a 3D or in graphics, it would be actually quite difficult. Similarly, you can see that on this like light bulb, as the camera turns, some of the background objects get are because the glass is transparent, you can actually see some of the shelves on the background. And similarly, you can see as the teddy bear wobbles in this ocean, some of the like water reflections get like resurfaced, like showing how this bear works. And similarly, you can actually show some of them, like this case of a macro shot of a like a of a some kind of a leaf or cocoon leaf, and as the camera turns, you can see more of the lights getting shown like across it. So the model also clearly not only learns steps, which is like relatively easy or task to identify, but also slightly harder task of doing like light transport in a reasonably realistic manner. And uh, because we worked on Nerf before, so naturally we wanted to compare like how it does like when compared with like 3D reconstruction based like techniques such as like Nerf. So here is a particular example where we captured 100 images around this particular coffee machine, and like we do 3D reconstruction on this coffee machine. So you can actually see some of these like a light being like you know on this metal surface of the coffee machine being like reflected on the surface. And on Dream Machine, we actually just take one image and do image to video, and the scene actually was looking reasonable. And you can see on the coffee machine, the kind of the metallic reflections like still gets like reflected as you turn the camera. So it means that on this like surface that is relatively reflective, things look the way things look kind of makes sense. And it also the metallic surface behaves very differently from the piece of wood that's on the table, because the wood actually is not as not nearly as like reflective. Similarly, you can see that basically there is the case of like learning like very cool dynamics and the transitions with water splashes and these kind of things, and with the teddy bear like bear fur and all the sorts, it is actually pretty cool scene. And some of the cases you can actually take like real life images of objects, and if it's not prompted, then it's like a AI generated video, it actually can get pretty tricky to notice that this is like a AI generated cat instead of like a real cat. And similarly, you can actually use it to generate a very like non-trivial camera transitions. So it is unlike, previous video models where are based on only a few frames, it actually allows you to generate like many frames and it like with like camera controls. And similarly, you can see some of the, uh, like shadows being like transported into different like behind this giraffe, the shadow is also moving as this camera turns and the giraffe is moving. So in this sense, it's obviously not perfect, but it is like somewhat realistic as to like how this relationship between the giraffe, the sun, and the shadow. And similarly, you can, generate some kind of a like dynamic situations such as like a smoke, fire, and like paper falling around. And you can use it to generate some interesting things like a clothing like simulations. So basically, again, these would be like pretty difficult to reproduce in like traditional graphic settings, whereas in video models, uh, it can be done. Another interesting thing that is entirely out of the scope of maybe perhaps um, graphics is basically, like causality. And this causality is more like less about like physical causality, but more on like a deeper level. So for example, in this particular video, it shows like initial uh like shot of this monster, and then it cuts to the next scene containing the same monster and an interesting forest. And you can see that the monster is kind of shocked or in awe, possibly due to this forest which evoked this emotion of the monster. And similarly, you can see that this girl is like very terrified by what she has been seeing in this first frame, which is a very, scary eye. And you can look at that the girl has very short hairs and a blue dress. And this, short hair and blue dress actually was also consistent with the first scene. Another thing again is like, this, kind of video model also is able to dream out like reasonably looking conditions, even in this, like fantasy world that is not physically like possible. So, for example, in this, like painting, you actually can also generate some like camera transitions. And similarly, you can like put in very like abstract things and you're still generating something that is like consistent with like tells you a story. So I hope I showed I have used this to demonstrate that like video models such as Stream Machine is very powerful and it is able to be used to generate a lot of the like learn a lot of the emergent capabilities, and these emergent capabilities include depths, it includes some light transport, it includes some like materials and dynamics, it includes some causality. And again, I would say all of this is just based on like simple a diffusion model, and it is mostly like the power of transformers and diffusion models. So uh I guess then the next question is like, what are, like, how can we, do even better? And what are some kind of useful techniques to think about in the context of like research community and, in the academia? So there has been always this debate between like autoregressive models and like diffusion models. And I started this, you know, uh, I started the talk by introducing autoregressive and saying that the diffusion model is this like alternative, and there's countless people have trying to make uh autoregressive model work in image and video generation cases, but unfortunately most of these like results don't actually lead to like better quality results. Simply possibly because of like tokenization in the discrete space is just generally harder for continuous signals. So a very natural idea is like, why not use both? Like we know that diffusion model works very well with images, and we know autoregressive model works very well with text. So essentially, you can just train one model that actually does both, and it's just a two different tasks. And for the text task, you could just do next token prediction, and for the like image task, you do diffusion. So that's basically it of the idea of this paper called transfusion. And like it has this like one multimodal model, and it tries to uh, produce like like a sequence or try to learn from a sequence that is interleaved, you know, like text and images. And this is a paper from Meta, but at the same time, a lot of like different uh, you know, like universities and research labs have their own versions of such multimodal models. Of course, similarly, not autoregressive models is not all lost. So there are also still these works like, for example, called visual autoregressive modeling, which tries to leverage the uniqueness of like visual domains. So basically, because we know that images like act in this multi-scale, so it is usually easy to predict a lower resolution scale with less tokens, and then predict the next scale which has like more tokens. So in this case, it's actually also some idea used in diffusion models where, like in original diffusion models, people try to use cascades where you first predict a lower resolution version and then use that lower resolution version to guide higher resolution generation. And again, another type of idea that comes between like that mixes autoregressive models and diffusion models are, for example, this work called diffusion forcing. So instead of trying to treat, you know, uh, instead of trying to treat all this like frames in the sequence to be the same, it I actually treat different frames of different frames like differently. So for example, you can think of this noising process as also masking. So as long as you add enough noise, then you lose all the information about this frame, and then this basically is like kind of a just masking procedure. Uh, and what diffusion forcing does is basically, uh, you know, instead of trying to, mask everything or like noise every piece the same speed, it actually you can try to noise different pieces at different speeds. So for example, you try to generate this, sequence in a nearly autoregressive fashion, and for the unknown part, it has more noise, and for the more known part, it has like less noise. So basically, you apply different noise levels onto different parts of the sequence. And this is obviously different from, the traditional like autoregressive generation, where you just keep like having this like uh the same like noise level and do generation autoregressively, or the full sequence diffusion, where basically every sequence has the same noise level. Of course, this like video models are not without their faults, and for example, like many people criticize that these models actually don't follow the like exactly physics. So for example, this is a image to video scene that tries to kind of do LK99, and basically it shows that after a flash, this rock suddenly becomes higher, and there's some like weird lightning going around. And it is possible that this error is caused by the model thinking that there is like a short change. And similarly, in this image to video task with a clever data set, the model actually does a very interesting kind of a like optical illusion, in which like it merges things, like move the cube around, and then have like have things just like floating in and going back. So what is actually interesting is as the cube cylinder goes up, the shadow also goes up. So the model is like definitely not perfect in terms of like learning these physics, but it's certainly also learned something. And like for example, there's also the case of like trying to like control the cameras better, but I think this is can be mostly solved by data. And another problem that we often see, like working on the 3D and videos, is this problem called the Janus or the multi-face problem. So Janus is a god supposedly has like multiple faces, and if you have worked on like text to 3D using techniques such as like SDS or score distillation sampling, this is a common like problem. The problem is basically that you're trying to optimize a problem where this 3D object has multiple views, and each view tries to match this image uh match the image model. But like the image obviously look at like front faces more than like backs. So the 3D object will actually have multiple faces. And similarly, we found that some of these cases also appear in videos. For example, in this particular car or in this particular bear, there are multiple faces that appear in the object. So interestingly, like video models also have this like problem that are common in 3D. And similarly, as the speed goes very fast, there's some like morphing effects that are like sometimes like just you know natural at some part and just suddenly becomes unnatural in like other parts. But again, I suspect this is something that is closer to how hands would converse in like image diffusion models like 2 years ago, and it probably can be fixed by like more data. And of course, we talked about how video models can be, a good avenue to getting to like 4D generation. So like then what's like how do we actually do that? So I think a lot of people actually are already collecting data sets really related to that thing. So for example, this is a like EgoXO 4D dataset where basically it shows from multiple views how this particular person does the same thing or inside the scene. So essentially, this is like a multi-view video, and it's like a multi-view like a image, but in like multiple dimensions. And of course, uh, similar to like text to 3D, where the multi-view image part is just like four views. In principle, you can also just use similar approaches to like fine-tune a video model and generate like 4D scenes. And that actually has also been done in the research community over the past few months. So before I conclude, I want to say like special thanks to the folks who developed the Dream Machine model. And if you have any questions, just send me an email at jiaming@lumaslabs.ai. And we are also hiring, so if you're like interested in joining, like please just send me an email. Thank you. I think that's it. Thank you.
Yeah, thank you very much. Thank you for the very great talk. So we also discussed some of the topics that you mentioned in the talk about like some 3D generation and some combination of the photorealism model and the diffusion models in this class. But it was really kind of the great summary and also giving lots of the insights for those topics. But thank you for the great talk. So I guess the audience might also have some lots of the questions for the Jiaming's talk. So maybe we can have some Q&A sessions. And
Yes, certainly. Yeah.
and while we are waiting for some of the questions from the audience, maybe I can start with some questions. So actually, yeah, most of the results were like really impressive in terms of like making some very realistic the videos. And I also agree that the video digital models can replace many kind of some graphics applications in terms of we don't need to render some 3D, 4D things, but we can just make some kind of the videos as the outputs. But I was wondering like how the Luma AI, the team is like handling some kind of some issues in the controllability for the video degeneration. So as you mentioned, like the user might want to have some kind of the controls. Like if we really want to like replace some kind of the game engines with the video degenerate models, then the user might want to basically changing many things, not just like giving some kind of the text, but rotating the
Yes.
camera, but like moving some of the object, or like making some kind of the changes in the shape, whatever kind of things. So for those kind of the controls, the question that I had is that while we have some like tons of the videos in the internet, I guess there are not many kind of the large scale data that are basically pairing those kind of the condition with the videos. So in terms of that, I guess that would be quite challenging problem, like, having this kind of the controllability, like how we can train a kind of the generic model that can basically takes these types of the control as kind of the condition. So yeah, that's one
Yes.
question.
Yes. Yeah, that's a very great question. So, I think one of the like, very common themes in like that I've mentioned is that, for image generation domain, we learn from like LMs, and I would say similarly for like im video generation domain, we will try to learn from like image domain. So on image domain, I think one of the greatest discoveries last year is like control nets. So basically, it shows that basically you don't actually need a lot of like data, and you essentially can leverage the models like innate capabilities to provide these kind of control, even though the model hasn't really been trained on like at large scale on these things. So I would assume that like in order to give this type of a control signal to the videos, one way to do this is also do like things like control nets that allows you to take the some signal in and provide the video signal out. However, uh, another yeah, like basically, I think that's kind of the easiest way that one could get to there. And of course, what kind of data that can be used in this scenario. So like one example is like, Luma's capture data. So in the capture data, you basically have like reconstructed the 3D objects in this scene. So in theory, you can just use it to render the entire, like you render anything, like any camera trajectory. And not only the camera trajectories, like extrinsics, but also intrinsics. So basically, you can actually use the models, like the 3D assets to generate scenes such as like dolly zoom. And basically, and it will be a pretty reasonable case to do. But of course, if we want to go into the route of like making it like again like ultimately super scalable and very dynamic, then yes, I think there's more like the some of the techniques based on like SLAM or like like post estimation could prove to be very useful here. Yeah.
Yeah, I think that would be quite interesting direction. So we have some questions in the Zoom chat. I guess it might be also good for you to check with each of them. So the first question is about um, yeah, stuff like extending the pre-trained video, the jet models for some kind of the some downstream the tasks, some like more applications like editing, segmentation, and so on. Mm.
Yes. So I definitely agree that in this case, like video models can be extended to like other downstream tasks. And in fact, that's kind of the point when I initially tried to say about like depth. The model certainly knows depth, and I think there has been some works already that tries to do depth estimation, like from pre-trained, like image diffusion models. So, for example, in this year's CPR, there's a paper called Marigold that tries to do that. And the the yeah, and so I think basically, the model, I guess the examples I show in this in the illustrations is to basically show that the model does actually have knowledge about this kind of like implicit capability. So like other than depth, the model certainly also knows segmentation because it knows the foreground and the background, and it also knows how to kind of generate things that were uh like not on original view and will kind of in-paint some like new views. So I think it can certainly be extended to this downstream task. And similarly, just similar to how people have used diffusion models to address some of the kind of image understanding tasks, I think video models can also be used for such downstream tasks. Of course, there is the matter of like cost efficiency. So the models currently cost a little bit more than what you would naturally desire. So for like real, like I think it's certainly doable in an academic sense. For like kind of a production level sense, maybe I think currently most of the like existing techniques still probably work like better in terms of the cost and like like quality frontier.
Yeah.
Yeah.
That's good answer. The next question is about the modeling the physics, the knowledge. So the question is about like whether we need to model
Yes.
the physics knowledge like more explicitly, or we just need to train the model more with some more videos.
Oh yes. So I think I mean, it doesn't have to be a like a or question. So, for example, the model can definitely be improved by watching more videos. Like I think that certainly the case, given the fact that we can, have better image like models by having, like over the year, like over the past 2 years by like having the image model like be bigger and look at more images. So this is part of where at least scalar law still currently works. And like I think over the like 2 years ago, people were complaining that image model doesn't really generate hands well, and you would say that uh, sorry, uh, and people have come up with like many kind of tricks to try to improve this particular cases, but eventually, like most of the methods are like quite simple and it doesn't actually involve designing a hand specific like objective function. So the reason why this is the case also is similar to maybe how language model is able to have immersion capabilities. So basically, there are like different tasks, and some tasks are easier to solve, and some tasks are like harder to solve. And a bigger model is certainly like has the capacity to kind of solve harder tasks. And like as you train more, the model like also begins to solve more of these tasks. So I think like scalar law to some extent I think will work. However, you know, being able to have some physical knowledge is also like quite useful for video generation. So for example, if you want precise control to the generated video, such as like for like game engines, then of course you would need to some kind of physical knowledge. This physical knowledge might just be like graphics. So for example, you need to know the camera locations of um, the camera locations. So for example, the camera extrinsics and intrinsics. So like having some knowledge here is certainly like very helpful for further model as well. But the way I mentioned it was like less dependent on the like changing the like core architecture with this transformer. Of course, in the text to 3D generation route, people also tried methods that leverage explicitly like 3D representations. So for example, in the Envy Dream case, I mentioned that in people generate multi-view like images, and these multi-view images are connected by just full self-attention, which was quite straightforward. However, I think there's also works that try to leverage the fact that where these like the camera like intrinsics and intrinsics of these like pixels are coming about. So basically, it allows you to, and basically it means that like the model kind of knows the different like how like this on this view how it matches the other view. So that kind of knowledge can certainly be leveraged, but I think the the benefit of like building this engine or building this like prior knowledge into the model is not as big as one may think. And it can help a little bit, but like together with the fact that this also becomes like harder to work with on like GPUs, it's like certainly very different. So I would say, I don't think this is a either or question. Both are kind of important, and like we can definitely make the model better by doing both.
Yeah, I think that's really kind of the open question. The next question is about also the 3D, 4D representations. So you also mentioned
Yes.
the work about like 3D, 4D generation. The question is like, what would be kind of the most effective, the preferable, the representation?
Oh, I see. Yeah, that's a very great question. So, I would think like many of these methods all have their like relative advantages and like disadvantages. So I guess a mesh-based representation is very good for things where you want to combine it like with like autoregressive generation or like a language models. So you basically just generate the vertices and generate the like edges. Like I can model this via LLMs, and basically it allows you to generate reasonable stuff. But of course, with mesh, there's the topology becomes an issue. Like it has to be, it has to satisfy some topology. Voxel representation is also, basically just a 3D version of an image. So it is also very good in the sense that you can use it to, like it you can like use it for like generation just like how you would generate images. But of course the problem with like voxel representation is that it's very high dimensional. So there is if you do 256 by 256 by 256 kind of okay, but maybe if you have like 1K by 1K by 1K it becomes like harder to deal with. So there also has been some work that tries to just learn latent space of voxel representations and tries to drive down the computational cost, similar to how like image and video models are doing compression. So I think that part can still reasonably be solved. In terms of like 3D GS, it's very powerful in the sense like how you like render these, and it's definitely preferable than Nerf in terms of like how you would render these. And of course, the rendering equations in 3D GS is like a little bit different than Nerf. So both have their like relative advantages. In terms of like 3D reconstruction, again, like or like 3D generation, I think both like 3DS and the Nerf also like all appeared in like countless papers by now. Perhaps maybe nowadays like people are using more in 3DS because of the efficiency reasons. So I would say for like 3D representation, there's just these all these representations exist for a reason, and like unfortunately like I wouldn't say there's a like preferable case that I personally find. I just find that, whatever suits best for your use case is the one that you should pursue. So if you care about like combining that with like your game engines or like downstream pipelines, then having mesh is certainly important. But you can also convert mesh from NERF or CDGS or voxel. These different representations can also be converted from one or the other. Of course, there's a quality degradations or quality differences, but yeah, it's certainly possible.
Yeah, pretty good. So the next question is again about some physics below. I think you already partially like answered the question, but the question is about that, there was like paper that says that the video generated models are like kind of like overfitting some kind of a physics law that they have seen in the training data. And how can we resolve those kind of issues?
Uh, Yeah, I mean, to be honest, I don't really know. I think this is a like natural problem in like machine learning, and like in machine learning, there's this like generalization issue that is you know that's always there. Of course, there is a possibility that some of these can be addressed with more data, and the of course some of these can be the case of like giving the model more physical constraints and of the things. But on the other hand, maybe we are asking a lot of the models like at the moment. So for example, like for humans, you wouldn't expect them to just kind of like hand draw a video for you. Most of these are still captured by cameras and things like that. And maybe if you try to kind of imagine or like recreate or draw a scene or a video, it's probably very physically like inaccurate either. Like even drawing pictures, I think it takes years of like learning and practice to kind of do it well. So I would say that humans are great at uh like telling differences or like discriminative things, but maybe humans are actually also not that great at generative things because if they were, people don't spend years learning how to be artists. But on the discriminant side, I believe that the model actually is also able to already do pretty well if we are providing it the right kind of downstream training. But yeah, the it is an open problem, so I think this I would hope that you know both methods can get us like models that are higher quality.
Yeah. And the next question is about like the synthetic data, how much the synthetic data will be helpful for improving the quality of the video generation.
Yes, that's a good question. So I think in some sense it certainly will help. So for example, in the case of like in the case of like trying to do camera control or like render scenes that are have like movements and stuff in it, it certainly will help. But of course there is this matter of like sim to real gap, and like synthetic data will help like in certain cases, but not necessarily work for cases that are hard to create. I think for language models, like things that are easier to kind of create synthetic data for are the things that you can verify is correctly, such as like code or math. But for other things, it's actually trickier to generate synthetic data because, well, if we knew how to generate the synthetic data, we wouldn't have like a machine learning model in the first place. We wouldn't have to use machine learning model in the first place. So I think physical 3D simulation could certainly help something, such as the camera, but it also has like limitations in terms of like this is actually different from like the real like reality. But as you can see, like most of the tech to 3D kind of works actually leverage synthetic data from uh you know in 3D to kind of improve the model's capability. So I think it will certainly help. It just needs to be controlled how much you want to deviate like into this like synthetic data side.
Yeah, and the next question is also about the super resolution. Whether the generative model can make some like high quality images with some various the resolutions.
I see. So in the field of super resolution, uh, I think a single model generate high quality images across variable resolutions. That actually has been shown. So like you can actually train the model to like just at a different resolution, then it can actually generate high quality images across the like various resolutions. For resolution, it hasn't been seen during training, so there's some extent of like generalization, but of course it's not perfect. And but like usually speaking, like interpolating between the resolutions or the aspect ratios you have seen during training certainly like works to a bit of extent. And the the next scale predictor in super resolution, I think I guess most folks don't use the same model for like super resolution at a different scale, mostly because of like efficiency reasons. So for example, if I use the same transformer for, like predicting 256 by 256 versus like 1K by 1K, I already have like 16x more like sequence lists. So like computationally it's just going to be less e efficient. The other thing is about like utility. So for super resolution, there is an extent to which like humans cannot tell like the difference. So like humans' eyes has like a limit on like what the resolution it can accept. So it certainly doesn't have to be like an infinite resolution. And I would say that for some tasks it becomes like unnecessary to do like to use diffusion models to do super resolution. But there are some tasks where diffusion models are very useful for super resolution. And for example, if you try to upscale from like say 64 to 64 to 256 by 256, this is a task where the model has to kind of imagine a lot of the details. And this is kind of the case where having a generative model is like very useful. In this case, it can be slow because diffusion models are just naturally slow, but the task is also harder. On the other hand, if you're talking about cases like a NVIDIA's deep learning super sampling, so basically you want this thing to be very fast and in working on game engines. So, but also instead of trying to generate from 64 to 256, you are mostly in this like case of like a one like a 1080p to like a 4K. So you just like you're already having a very high resolution scene, and then you want to just two by two upsample the resolution. And in that case, typically you don't need that many uh you don't need like that powerful model because well your model also has to like run on real time. So as a result, they also try to like have game specific models. So the solution can depend quite differently like for like, even for super resolution on like depending on the problem. So I think although that being said, I do think there is uh it is certainly possible for one single model to do multi type of like resolution, super resolution tasks. But at certain level, the utility of like doing super resolution for like super high resolution in diffusion models becomes like lower. Yeah.
Yeah, okay, we also discussed like how to solve the inverse problem using the pre-trained diffusion model in this class, including your paper, the PyGDM in this class. So yeah.
Oh yes. So in my paper, basically the idea was that basically in classifier free guidance, you basically try to treat the diffusion generated process as like learning this like gradient of the log probability. So you have the gradient of log probability of your base model, but then you P of X, let's say. But then you also have the conditioning, which is like a P of Y given X. And basically in super resolution, we can just come up with a constraint. So we want to generate our constraint is basically that I want to generate some X that is close to the data distribution while when being downsampled, it is this, like a lower resolution image. So if you don't have the constraint, then we'll just generate a random image that doesn't do your super resolution task. So basically, in my paper, and I think in the like some other papers, the goal is to basically try to approximate the term that is the log probability of y given x. So there's like different versions of like trying to approximate these things, and like my work on PyGDM is one particular way of doing this without going to too much details. So I guess the benefit of that is like you can actually use a pre-trained model and do these different tasks at the inference time. But of course, with things like control net, you can actually also just train these tasks like a priori or like using not as much compute as you would expect, and this could also solve the problems in a reasonable manner.
Yeah, thank you. I guess we can also combine the next two questions, like both are about like but the ability of the video diffusion model, the generative models in terms like understanding the causality and many some physical laws and many things, and also having some kind of the capabilities of like some precise the control. I think you also partially answered those questions, but
Yes. So I guess in this case, basically, yeah, these are kind of just ongoing questions that is on the like, video generation model community. So I think one of the some of the techniques I think is similar to how you address hallucination in large language models. So certainly you wouldn't say like large language models are you know like perfect in terms of like what they like produce, but the responses certainly get better and better as you improve like post-training techniques. So for example, you have like supervised fine-tuning and also like RLHF type kind of techniques that can be used to improve the quality of the models. Of course, uh the the like similarly for like video models, I think like because this surreal or dreamlike representation is basically I think the hallucination of the model. So uh from a perspective, I think using more of the post-training techniques that language models inspired us to certainly will help improve like reflecting some of these like principles as well as the like causal relationships. Uh, Although I do have to mention that uh, there are just the different approaches to solve the different problems, and they're getting like even getting uh some of the principles or causal relationships into the model doesn't have to involve like building this into the model. It can be more like oh, I generate data from the simulator that actually be used as synthesized data that helps like guide the model. Whether it will like you know entirely solve the model, I don't know. So it's hard to say. The other question is like can the model precisely control like physical properties? So the I guess then the matter of question is like how precise you want to be. So I think like there are certainly cases where it is good to like some people and maybe not good for like some other people. So for example, like I cleared like this year there's a submission called IC Light that actually tries to use like like change lighting in the images. So certainly some of these techniques can also be used there. So I would say like the models can certainly be used to control physical like properties, but how precise is like hard to say because like in real physical worlds, the measurements are also like quite noisy and imprecise. So, for example, in like cases where you go to like a microscopic manner, or like you have just like uncertainty principles where like yeah, like just measurement is like not always precise in like physical worlds as well. Uh, so in that sense, I think like data can certainly help. So uh, and but to how precise is something that we would really can only like experiment upon. Like we need to do the experiments to know like how much they can do. Uh, yeah.
We have like one new question about some details about EDPM.
Yes. Yes. So in the DDM paper introduced, yes. What might happen if the variance is increased further? So the yes. Okay. Okay. So I think in that case, it's really it doesn't satisfy mathematics in the sense that it will give you a reverse process that like uh exactly reproduces the kind of the reverse diffusion process in the DDPM case. So I would say this is like tricky to reason in like the math case. But of course, just like people are using some things that are not necessarily precise in math. So for example, in classifier free guidance, it's actually also not precisely like measuring like correctly the exact kind of a conditional like score like functions that you use to like sample from diffusion models. But nevertheless, people find it to be super useful in practice. And I think that similarly for these kind of applications, the reason why you would add a lot more noise is simply because that the 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 kind of the model prediction is further from the truth. So if your modeling is precise, then using DDIM should be like better. And this has been shown in like Taro Carlos's like 2022 like New York Spec paper called like elucidated the diffusion models called EDM. So in that case, they specifically did an experiment where they have a very, very well-trained diffusion model, and they test different types of like samplers, such as the DDIM, the deterministic ones like DDIM, and like non-deterministic ones that add noise. And the finding was that adding noise adding noise certainly hurts if your model is like extremely precise. But of course, if your model is not precise, then adding noise helps in terms of like, helping uh, to like be more robust. So the model becomes more robust as it becomes like more precise. So that I think is the main differences. And the image in painting task, basically the noise predictions are just a very heuristic and very imprecise. So adding more noise probably just helped in the sense that it will like mask out the imperfections of the prediction and it's just generally more robust.
Yeah, thank you. Yeah, it's really good to know to learn those things from the author of the DDI. Yeah, thank you. I'd like to wrap up this session with the one last question. I'm just wondering how you envision the future of the generative AI, the technique, and for the next like 3 years or the 5 years, like what would be happen? And also, I guess there might be many students here who might be dreaming of some kind of the career in this like field of the generative AI. So I just want to ask you to give some kind of the a bit of the some kind of the advice in terms of how they should also prepare their the future.
Yes, yes. So I think at least for video models, I envision that the future is going into like similar trend in like large language models. So like pre-training, post-training, and going into these directions. And solving the efficiency problems of video models certainly is also very important. And being able to have as I have listed in some of the future works, being able to maybe combine diffusion models and the autoregressive models and having uh, you know, which like taking the advantages of both sides is also going to be quite interesting. So as for like career-wise, I think it's they're like if you're pursuing like a PhD program, then perhaps like the more reasonable choice is to do like research scientist or do go into industry or go to academia. And in this case, going to academia requires like more like papers or groundbreaking papers, and going to industry not as much, but a lot of the kind of industry like or like knowledge. And I think depends on what you want to do. It's certainly like a slightly different set of skills. But I think as we go into this like more foundation model kind of skills, like things that are like more practical, such as on the data side of things, as well as like like ML infra side of things, become like actually at least a lot more like relevant than what I was doing my PhD. Like my during like my PhD, we only have like 2080 as the GPUs, and I did all the like DDIM experiments on like four or like two like 2080 GPUs. I had no almost nothing about like distributed training, and I was actually mostly just using like like data parallel instead of a distributed data parallel in like PyTorch. So like certainly I didn't know much, but I think at this day and age, like it is very important to be able to kind of embrace the like change that has been brought by foundation models, and like them being kind of like learning fast, and like being able to kind of take uh like learn new things quickly is certainly going to be like very important in this like very rapidly like advancing age. And yeah, I don't have very good specific advice because I think like the the situation is different every year, and this also like the field is also becoming like a more and more competitive, and unfortunately less kind of acceptable for like like ideas that are like a smaller scale but like really novel. But I think at least working like along the lines where the general trend is going is going to be helpful for like coming up with like research ideas or like pursuing a career like in the field. And another like final piece of advice is like I think like eventually people like uh, as is the case for me, like people remember you for the most impactful thing that you do. And similar for me, like I have like probably like a 30 or 50 papers during my PhD, but people mostly remember for TDN. So I think this is the same case regardless whether you go to like academia or going to industry. It's very important to kind of target for like high impact things rather than like spend a lot of time on like many incremental things. So yeah, that's it.
Yeah, thank you for the great advice. I think that'll be very helpful for the many students here. Yeah. By the way, are you attending RIPS this time?
Uh, Possibly, but I won't be staying long if I were to. But I haven't finalized my like
I
trip
see.
yet.
Yeah, if you're attending English now, I'll be happy to. So that's the video there.
Okay.
And thank you very
All
much.
right.
So
Cool.
thank you for the
Awesome.
wonderful talk and also all the insightful the comments. And also thank you for the audience for joining today. So yeah, let me
All
end
right.
it.
Thank you. Yep.
Thank you. Thank you all. Thank you.
Yep. Happy to be here. Thank you.
Thank you.
Thank you. Yep.
Bye.